Hello, hello, hello. This is Will. Today is Saturday, February 15th, 2024. Well, I guess logically it's still February 14th. We're after midnight here. Actually, it's 4:13 a.m. Welcome to From Bronze to GM and miniKanren, episode 7. Yeah. Well, I'm feeling a little off today. I think I read the news a little too much. A lot going on. So, yeah, I didn't really feel like doing anything tonight, to be honest. But I bootstrapped myself by watching some Vibe GM Bronze to GM. For Zerg, watched a little of that, and I laddered. I played some StarCraft 2 tonight. I got cheesed out a few times. That's fine. A random player named Noob Hunter DT rushed me. It was like, what a shock. Noob Hunter. The random Noob Hunter DT'd me. That's fine. I didn't get mad any of the games. I lost to some cheese, but I just tried to focus on my macro. I watched a couple other Vibe videos, and one video maybe he was playing, I think he was playing Warcraft 3, maybe it was tonight. And someone asked, how do you get into Warcraft 3? And he talked about it a little bit, and he said Warcraft 3, it's really more about the micro. There's not that much macro. There's where it says, he said, if you want to learn Warcraft 3, concentrate on the micro. If you want to learn StarCraft 2, concentrate on the macro, the economy, like building stuff, building workers and building units, and building production, all that is really what you want to focus on, is the macro. And he said this a number of times, and also that's kind of like, the foundation. You'll get cheesed out a fair amount when you're learning the macro, but that's okay. If you're going to lose, you should lose in a macro game, not, because you spent all of your attention in APM, microing 2 Zerglings, and you didn't make any drones. If you want to advance past a certain level, if you don't want to be forever bronze or forever silver, you got to concentrate on your macro. And, I was thinking about that in terms of undergrad thinking versus grad school thinking, or PhD researcher thinking, or whatever. It doesn't matter if you're an undergrad or grad student, or not a student at all, or in high school or middle school, or not in school. The undergrad thinking, we'll call it in quotes, undergrad thinking, is concentrate on grades and, what's on the syllabus, how do I get an A in the class, that kind of thing. Whereas, once you get up to grad school for like original research, like I said, there isn't like a textbook. You may be the one writing the textbook, or maybe your advisor is writing the textbook. And the grades don't really matter. That's not a big thing. And, you really want to get into research as quickly as possible. And so, I had friends who started with me in the PhD program, and, some of them didn't know what they wanted to do research in, or who their advisor was. So they waited until they had taken a whole bunch of classes to get into the research. And I was coming from the opposite standpoint. I had already done research, and I was super annoyed I had to take any classes before I could start doing research. It didn't take me very long to start getting into research. But I was like, let's go. Come on. I'm ready to go. And I think, I had very much the grad school researcher mentality coming in. Whereas I know some people who had just gone straight through school. They had the thought that being a researcher or getting a PhD or whatever was like an undergrad plus or something, right? It's like you do the same thing as for an undergrad, but maybe everything's harder or something. It was like, no, it's completely different. It's not the same thing at all. Okay. Like, an undergrad, you're perfecting, you're trying to get good at the things that people are teaching you, so you can go off and do something, right? Whereas like grad school, for at least PhD, you're trying to become a researcher who can stand on your own, and you can do original research, right? And you can work on problems that are just open that no one solved. And it requires a totally different style of thinking. So it's kind of the macro thinking. And from programming standpoint, programming might be the micro, and then all these research practices like, knowing the research literature and knowing how to write a paper and picking a venue and, knowing how to give a talk, picking a research problem, like trying to figure out how to get unstuck on the research problem, and then there's like a whole mental game, which I think is actually the harder part. It's like hard to do these things. Okay. So it's hard enough to do the micro part. It's hard enough to be good at programming. And it's hard enough to know how to write a scientific paper, or how to give a talk and so forth, how to pick a research problem. And a lot of this stuff's nebulous, like much more nebulous than becoming a good programmer. Okay. Like there, so many books and tutorials and boot camps and degrees to help you, say with the programming part, but the researcher part, that's what grad school was created for or whatever. And often involves very intense mentoring. Now, of course, to really level up for a programmer, often mentoring is really, really, really useful. But for the research, just because things tend to be more nebulous, like how can you tell if a research problem's good or not? How can you tell if you're making progress? If you're working on something that's like an open problem that literally no one in the world knows if the problem can even be solved, that's just a different thing than working on a programming problem that, is probably pretty tricky and maybe is hard to scope or to know how long it's going to take, or whether or not with the resources you have, you'll be able to do it. But, other people have done it maybe, or the, systems like it exist. So this is already just hard through being very nebulous. But then, there are other things that are tricky that just like kind of emotionally, mentally, in that you might be working on a problem for weeks, months, years, and not make any apparent progress. Now, hopefully you're not going years without making any apparent progress. That's probably too long. But you know what I mean? Like there'll be times where you feel like you've made progress, and then it's like, this thing didn't work out, or, I feel like I got scooped by someone else, or, whatever it is. Okay. It's just, there are times you're going to feel that way. Now, I think there are times you feel that way in programming as well, right? I mean, there are lots of things with programming, like lots of setbacks, and programming is generally difficult, especially if you're trying to push yourself. But, I think at the research level, it's even harder just because it's nebulous. And I guess part of it is like it can feel very lonely if you don't have a community around you. So I want to talk about that a little bit in a minute. The programming can also be kind of like that. Like you make something, you spend a lot of time making something, and no one cares, right? Like the research, I think, just like that's the default state. Okay. You're working on something, and the default is no one's going to care until and unless you can convince them otherwise, partly because maybe no one can even understand it, right? Like you're working on some problem where not too many people could even understand what the problem is you're trying to solve. Sort of just the the community is smaller. Like if you're a programmer working on a video game, let's say, if the game is good, people can appreciate that. For research saying, well, now like LLMs are super hot. So if you make some big advance with LLMs, like, people care. But for most people working, like think of, theoretical mathematics or something, right? It's like, if you're at the cutting edge, there may only be a few people in the world who really understand the problem you're trying to solve. So anyway, there's a very significant mental, emotional part of this. So I like to talk about that. But the other part is this idea of the grad school thinking or the research thinking. I think that's really important. And so that's why I keep emphasizing, it's like we're not just going to talk about scheme and miniKanren, although I am going to talk about scheme today in terms of lists and cons, pairs and symbols and all that. But I want you to really start with the research practices and the research thinking, like from the very beginning. Okay, we're not going to wait. It's like some of my friends who waited until they had taken a bunch of classes. They waited literally years before they decided on a research area, who their advisor was going to be, stuff like that. They waited years to start the research. Like, no. We're not going to do that. We're going to start like from the beginning thinking about the research part. Okay, so yes, I'm going to show you all sorts of scheme and miniKanren things. But I want us to be involved in these research practices from the very beginning. Okay, that's why you want a notebook. That's why you want to be reading papers. I was happy to see that at least some people are excited to read those history of programming languages papers, the REPL proceedings. Yeah, the REPL proceedings are great, especially, like going back and looking at the old languages. Those are languages maybe you have never seen, like jovial. Okay, that does way before my time, but it's very interesting to go and read about these things. So, that's what we're really going to concentrate on. That's like the macro part. Okay, the micro part, yeah, like how to do a cons pair, and you need that. Okay, just like you would in a real-time strategy game, you need some level of micro, but the macro is what really is going to carry you through in terms of pushing the state of the art, understanding what the state of the art is, communicating new ideas. Like this is where the idea stuff comes in, like the idea generation, the new idea, all of that. Okay, so we're gonna focus on that even as we learn our micro. Yeah, so the mental emotional resilience, like one example of this is there's a book I've read at least one book by Richard Forte, maybe more than one. One book was Trilobite. I think this is the book I read it in. But Richard Forte was talking about a researcher who had studied some specific subspecies of insect for like 40 plus years. And Richard Forte was asking about, what the I think is the answer. Okay, I'm not remembering all the details. Okay, but it was some researcher who had studied something like very, very particular, for many decades, and the question is, well, what does this person's colleagues think about that? And apparently, the colleagues are like, yeah, that's awesome. That's really, really hard. It's really hard to spend 40 years studying one thing. Okay. And I think that's true. Like when I was working on my PhD, I've got a very much generalist personality. I like doing lots of things. It's just like it was emotionally hard for me to spend 6 years working on one project. I mean, I guess maybe it's like 5 years or something, but that was really hard. And by the time I was done, I didn't want to have anything to do with miniKanren. So I took a little time off. It came back pretty quickly. But that was tough. And I watched some videos with Vibe, who started playing StarCraft 2 again, he was talking about how, he was a pro StarCraft 2 player. He played really intensely for a decade. He did I think he did at least two Bronze to Grandmasters series. It's done tons of coaching and commentating, all these things. And at some point he got burned out. Actually, I guess when he was doing the second Bronze to Grandmasters in 2021. And he's got a very interesting video where he talks about this for like 45 minutes. And part of it had to do with Blizzard canceling support, a bunch of people leaving Blizzard or being forced out. Blizzard basically not making, Warcraft 4, or, basically all the people who had built all the real-time strategy games at Blizzard are gone now. Some of them have started other studios and are trying to make new games, but will Warcraft 4 ever come out? And if it does, is it going to have any resemblance to the parts of the games that people liked before? I don't know. But when I was looking at his Bronze to GM series, and he had, I think for the Zerg stuff, like 22 videos for the 2021. I think there were at least 2 videos that were sort of generic. But if he did Terran, Zerg, and Protoss like that, that's like something like 60 videos. And some of those videos are, like 2 or 3 hours. So that's a lot, so he may have put in, 150 hours or something, like not including prep time or anything like that. And then, I think he did at least one other, I know he did one other series. I don't know, maybe that's the only one, but like he may have put in 300 hours of like actually recording time. Okay. Not prep time or editing time or anything else, like 300 hours of making these videos, like 300 hours of videos. And I think the second one took a lot out of him. He has no interest in doing it again. Now part of it is he is like, it probably takes like 2 months to do that, to do one of those series, at least a month, and more like 2 months. And he was saying, well, now I just want to play, I just like, I want to take it easy. Just want to play some. And I could totally understand that. And so tonight I was thinking, well, I could take the day off. I could take the night off. Do I really want to make a video? And, is this kind of doing the calculations like, well, for Vibe to do it, if it's taking like 100 to 150 hours, for StarCraft 2, how many videos do I have to make? How many hours worth do I need to talk about, like, getting to research level, right, and all the practices there, let alone all the scheme and miniKanren stuff? Like, that sounds like a big lift, right? This at least that big. That's at least 100 to 150 hours, to be honest. And is anyone going to watch that? I don't know. That's the other thing. It's like, who's going to watch that? So I'm looking at the YouTube statistics, which is probably a really bad idea. But it's like, for one of these videos that I made that was like 3 hours long, it's like average viewing time, 18 minutes. It's like, I know that's the average. Okay. So maybe there's one person who watched till the end, but that, I was like, oh yeah. Anyway, and that reminds me of this George R.R. Martin story, which, I don't know, maybe I can see if I can find it on YouTube, but it's great, where he's talking about being an author, how hard being an author is, a full-time writer. How hard it is to be a full-time writer. And he said, everyone, first of all, he says, if security is what you want, this is not the profession for you. But then the other part he said was, everyone imagines themselves or dreams about, having a book signing and, having a bunch of people in line. No one imagined, or no one dreams about, having a book signing and like no one shows up, right? And he said that when when he did the first Game of Thrones book. It's like, not only were there some signings where literally no one showed up, but he said there was one signing where he drove 4 people out of the store. The bookstore. There were 4 people in the bookstore, and as soon as he started talking, they all left. So he had like -4 people. Of course, this is like Game of Thrones, right? And he had been a writer, professional writer, for a long time. So I think that's like just kind of an example of sort of the professional, or sort of like the emotional resilience and stuff like that. Like you, that's like the more GG, more skill, right? From White Raw. A lot of it's just the attitude. So like I got cheesed out on ladder a fair number of times tonight, and I used to get really upset by that, and now I'm like, okay, that's fine. I'm just working on my macro. I'm trying to get my hotkeys down and getting my pace down, and trying to, pay attention to where my workers are, and how many minerals do I have, and spreading my creep. Like paying attention to that with the idea that longer term, that's what's going to get me. That's how I'm going to improve significantly. Okay. I'm not going to be forever low platinum, which is where I currently am. I've never gotten out of platinum, by the way. That's platinum's as good as I've gotten. So I very much want to get to diamond and masters, and, who knows, maybe someday GM. But in any case, right now I'm forever platinum, but I'm following Vibe's advice about how to get out of that league and what to focus on, right? So I've gotten to the point where like major/special, I don't get angry when I lose. Okay, so that's really important. So yeah, I felt kind of rotten today after reading the news way too much, and I didn't want to get out of bed. And I just watched some 80s music videos for a while and watched some Vibe. And then I said, you know what? I need some coffee, and I'm going to ladder. And laddering usually wakes me up, and that did. And then I felt like making this video, so that's great. But that's like every day. There have been times where I'm making a video every day, or more than one video, right? Like the KiloTube challenge, I was trying to make 1,024 videos in a year, and I was like, I don't really feel like making any videos today. Another example is there's a TV show. It's like SAS Who Dares Wins is like the British version, and it's like Special Forces World's Hardest Test is the American version or whatever. I think there's an Australian version, but it's about these like special forces people who are training, civilians and sometimes celebrities, sometimes like D-list celebrities. And the idea is that, okay, you have a bunch of people and they go through the special forces training, or ostensibly special forces training, and then you see who's left. And they do this for a few weeks. And it's actually really interesting to me because it looks, it's a lot like academia and PhD program, I think. It remind me a lot of that, where some people like physically couldn't do it, right? And I've had friends in grad school who got sick or injured, or there were other things, like they had maybe had to take care of someone, and like they weren't able to do it full time. Okay. And so they just weren't able to do it. And then for a lot of other people, I don't know. It's just like there was something else that was more appealing, or the lifestyle of like, not making money, and, you get a little stipend, but generally, the grind of it, not making progress, getting in arguments with their advisor, maybe all of these things is just like, there's a lot of ups and downs, and then, when you have the PhD, you still have your job search, and, maybe you do a postdoc that may or may not work out. Maybe you do faculty search, may or may not work out. You could end up being a postdoc for a long time. Maybe you got a family. You're like traveling around the U.S. on a postdoc salary. Trying to raise a fund. All of these things happen, and it's tough. And in these special forces, there's this idea of a VW, a voluntary withdrawal. Like at any time, someone can just say, I VW, and here's my armband with my number on it, right? And that's it. They're done. And when you watch the show, like most of the people are VWing, and it's interesting to watch them talk about it. It's like, I just started thinking about, I want to be with my family. Or I started thinking about, I really enjoy riding horses, and I want to go ride my horses or whatever. Like whatever it is, there's something not what they're doing that is very appealing, and no wonder, because what they're doing is not very much fun, and it's like really hard, and they're exhausted and hungry and everything else. And the people who get to the end are not necessarily the strongest or the most fit or the youngest people. In fact, it's often not that. Like sometimes you'll have like an Olympic gold medalist and who's just in phenomenal shape, and they like won't make it. They might not do well at all, or like an NFL player. Often they don't do well at all. And it's almost always for sort of like emotional reasons, or they're used to being, like physically the best at everything. I saw that a lot in grad school and academia. Like people, this is kind of the undergraduate thing. Like people who were just used to, being the best at everything in undergrad and just crushing their classes and getting an A+ and everything. And then they get to grad school or a PhD, and they're working for the first time in their lives on a problem that like no one knows how to solve, or even if it can be solved using their techniques maybe. And that can be tough. I've seen people really have trouble dealing with that switch. And anyway, so the people who finish this program, this training program, supposedly special forces, like there are a lot of people who are like, well, this isn't really like special forces training, this is like watered down. That's probably true. However, the case is like still most people don't make it through and they voluntarily withdraw. Okay, most people, they're not injured. It's not like they can't physically do it. They decide they want to do something else instead, which is a totally understandable thing. Doing push-ups in the mud when you're already exhausted and cold and everything else like that at some point is going to wear on you, right? But the people who finish, it's interesting to see kind of what keeps them going. And there's always something about it. And one of the special forces trainers says that, it's almost like you have to get up in the morning and say, like, I'm going to embrace this difficulty, right? I'm going to just like kind of, I know it's going to be hard. I know it's going to be miserable. Like, that's okay. I'm happy that I'm able to do it and keep going, right? Or they have sort of like, okay, let me get to lunch. Okay, all right, I'm at lunch. Let me get to dinner, right? That kind of thing. So just have a mentality that lets them stay in there, and I think that's actually like way harder. Like the emotional mental part is like way harder than the like knowing anything technical. at some point. Like it's just hard to do this for a long time, especially when no one seems to be interested, right? So like some researcher who studies an insect for 40 years, right? Like that person's got some resilience at some level. They had to find that, and and going along with that, I find that little bits of encouragement can go a long way. So with miniKanren, when I graduated in 2009 with my, finished my PhD, I can tell you at that point there was effectively zero interest in the academic world with miniKanren. So we wrote the Reason Schemer, the first edition, and I wrote my dissertation. But like the Reason Schemer, it's like one of these little books, right? It's like Socratic dialogue. It's like the little schemer, Reason Schemer. Those are not academic books, even though it's published by MIT Press. That's aimed towards the bright high school student or whatever. So, there just wasn't, a lot of interest in academia, let's say. But I got this nice email from David Nolan in the Clojure community, and he had done this core.logic library, and it turns out they were having ClojureConj. I think it was the second year of ClojureConj in Raleigh. And it turned out that there were 2 talks there on core.logic. And and I showed that to Dan, and as soon as I saw it, I'm like, okay, I'm going. And then Dan wanted to go, and we arranged it all, and we went there, and it was so different than the academic stuff. Like we were treated like celebrities, especially Dan. A lot of people had read Dan's books, and it was like very different than very different than the academic reaction, which was either crickets or like, why did you do that? There's prologue, right? So that the fact that there were people who were interested and were inspired by it to do something based on it, that really kept me going and wanting to do more miniKanren, because I thought, I've graduated, I'll go do something else maybe. So that was a large amount of encouragement. That was super helpful. I don't know if I'd be working on miniKanren or having anything to do with miniKanren if it weren't for that. And then for these videos, like these B to GM videos, a couple people, I think 3 people wanted to join the Discord. People were commenting, and a few people, not a lot of people, but a few people, and that was like, and I was thinking tonight, do I want to do it? I really don't feel like doing anything. And then someone emailed me, oh yeah, can I get the Discord invite? Right. And it's like, okay. That was like enough to get me out of bed. All right. So, and I know another story tonight about that, where someone who had been writing some software that was on GitHub. Apparently the software had like 2,000 stars or something. And someone, for the first time tonight, gave a donation or whatever. And the person was like, thank you so much. You're the first person who has, has supported me in that way, right? And so this is a project that's gotten actually a ton of attention. It's been around for a while, I guess. And so, for that person, the amount of money I think is not that much, but that was not the point. The point was that someone actually cared. enough to try to support. So my first thing I'll add to our ladder practice for today. Okay, let's go down here. The ladder practice is, let someone whose work you admire or has inspired you let them know. Okay, you don't have to give them money. You don't have to do anything like that. Just let someone know, and do it in a way, please, that's like authentic. Like, give them some specifics. Please give specifics. What about it, or like in which way, has it inspired you or whatever. But I don't know. Like, every once in a while, I get this out of the blue. Like that talk, The Most Beautiful Program Ever Written. I still get emails from people like, hey, I saw that talk, it really made me want to get into programming languages, or, now I'm thinking about going to grad school, whatever it is. Okay, it's not like something like that. It's like, oh yeah, I should make more stuff. Yeah, or like at Popple in Boston. Last time Popple was in Boston, sort of after COVID was dying down some, I had a few people come up to me at Popple and say, oh, those videos really helped me get through COVID, and, you're going to make any more of those, right? And, I don't know, that was super motivating. I mean, that's one reason I'm doing this, is that people at Popple asked me. It's like, just a few people. It's like maybe 3 people. But that was enough. It's enough to have 3 people. So anyway, if there's someone whose work you admire, especially if it's someone who you think probably isn't getting a lot of feedback, but who knows? I mean, even people who you think might get feedback, like that person had 2,000 stars on their repo, apparently wasn't, like a star on a repo, that's a cheap thing, right? But like an email out of the blue with some specifics, that goes further. So anyway, I think that can go a long way for someone to realize it's making impact. And the other thing I was thinking about is, one thing that makes it, I mean, it's already hard to do research, right? I mean, it's just hard by its very nature. It's even much harder if you don't, if you're not part of a community, and that might be because you're outside of academia, or you're outside of that research circle, or it could be because you're doing work in an area that's so small, so niche, there are only a couple people, right? Like, there may not be much community around it. So I'm trying to think about that, and also I'm trying to think about mentoring. So, that's like a really big thing. Okay, so people who go to grad school, or people who are like undergrads at fancy research schools, they get mentoring, at least if they're doing research in general. And in fact, at some fancy schools, like they might, an undergrad might have like 5 or 6 mentors, or more, and that's a big deal. And there are some mentoring programs, like ACM has, like SIG Plan has the long-term mentoring and so forth, which I've participated in. But I think that program is more for people who are trying to go more academic, or maybe get a PhD, or at least considering it. I know a lot of people who might watch this or listen to this would be, maybe not in that situation where they're thinking about getting a PhD or going to grad school for it. So how to help people with mentoring, if they're not in that situation, or if they're not at one of these universities or whatever, if they're not a student. So anyway, I've started thinking about it. So we've got this Discord. It's been pretty quiet. It's getting a little more active now that I'm making these videos, but I've been trying to think about the mentoring and the community stuff. And, I could probably do some level of mentoring, but, I can mentor like a handful of people maybe, or like one or two, or maybe three, like in a significant way. But if this ends up being popular, right, maybe that's all it is one or two or three people. Maybe I can mentor those people. But if it ends up being more, I don't know, I need help, or or we do some sort of peer mentoring or something. I don't know. But the mentoring is so important that's maybe there's some way to set it up where we can find other people who can do mentoring. And then the community thing. So there's like a little Discord server that we have. I'm not sure. I'm just starting to think about this stuff. If you all have ideas or suggestions, please let me know. Okay. So we'll get into some scheme here, but let's look at our previous ladder practice. So learn your powers of 2 up to some credible number. Like you should know up to 10 to the 10th is 1024. And this worth keeping in mind. 2 to the 10th is approximately 10 to the 3rd, which is 1,000. 2 to the 20th is approximately 10 to the 6th, is a million. And 2 to the 30th is approximately 10 to the 9th, which is a billion. And if you know those and your powers of 2 up to 2 to the 10th, you can do math in your head about, order of magnitude stuff, which is quite helpful. Okay, read up on signed and unsigned 2's complement integer representations if you're not already familiar with that. Okay. And then, read up on the Ariane 5 and Patriot missile battery mishaps. And then think about difference in design between Scheme and Java when it comes to integers, overflow, etc. If you know languages like C, you might think about what's the difference there as well. So starting to think about differences, and we're not thinking about in terms of good or bad, we're thinking about trade-offs. And I like this Joe Armstrong idea about, you think about the intent of the language designer. What were the problems or domains that the language was intended to be applied to? And given that, do the trade-offs and the design decisions like hang together? Okay, do they make sense, or do they seem kind of haphazard or random? And I was, saying that for me, for Java, it seemed like, there's this thing where, array bounds are checked in Java, so that's a safety thing, and there's garbage collection. You don't have pointer arithmetic, so there's some safety there. But when it comes to integer representation, first of all, there's a bunch of ways to represent integers, and they don't all work together, although the automatic boxing and unboxing helps. But this integer overflow thing, which, that's very assembly language or machine code, C type thing, that the safety aspect starts falling apart, when you have integer overflow, in my opinion. Now, it could be very expensive to check it, maybe when Java was first created, that was a trade-off where performance-wise they weren't, able to make it, or say, okay, well, use big integer or something. Anyway, that felt to me like a trade-off that was unfortunate. Okay, let me just put it that way. And then it was also interesting to see that for Shea scheme, that when you had the overflow for a fixed num, that got, there was an exception. And I think, so we found out the R6RS has, fixed nums in it. I didn't know that. So I guess this behavior is part of the standard, worth looking at. And then of course, scheme by default, like the regular, integers are just, those are big nums. So there is no such thing as overflow. But you can run out of memory. Okay, it's possible to run out of memory. And so the numbers could be so big that you actually run out of memory from the numbers. Okay. What do you do then? Yeah. So that's a different trade-off. Anyway, so worth thinking about those different design decisions and, what your thoughts are on it. Okay. All right. So starting to think about language design. Okay. So now let's, get into the micro parts of it, because we talked about the mental game and all that. Keep up with your research notebook. That's part of the macro game, and keep reading papers. And if you're inspired by the history of programming languages papers, look at those. Make sure you watch those videos by Simon Peyton Jones on giving a great research talk and writing a great research paper, because we're going to want to have outputs, communication outputs of our work, right? This has nothing to do with whether or not you're an academic or whether or not you want to be a pro. Okay, you don't have to be a student. You don't have to be in academia. The point is, if we're doing research, which is where we want to get to, that level where we're thinking of ideas and trying to improve on ideas, explore ideas, we want to be able to communicate those ideas. Now, the fact that you know how to write a scientific paper and pick a venue and submit the paper and go through, the peer review process and all that, that doesn't stop you from writing a blog post or, giving a talk somewhere else or doing something that's less formal or less academic. You can communicate things many ways, right? That doesn't stop you. However, if you don't know how to do the academic thing, then if it's important to you to have that sort of feedback and to maybe have an impact on the community that way, the academic community that way, then it's going to be tough, because that's a different set of practices, different set of expectations, different way of communicating. So I want you to know how to do that, and then you can choose whether or not you want to do the academic paper or not. It's up to you. If you want to have if you design a language, let's say, and you want to have a semantics, or you want to have something more formal, or you want to present that to an academic audience, should be able to do that. And another thing, of course, and this also goes to community and mentoring, is if you've never written a paper for any sort of academic venue, then it's really helpful to end up writing with someone who has. Okay, so that's where a lot of the mentoring comes in. So for a lot of people, their first paper is going to be with someone who has experience. Okay. Let's talk scheme. So we've done a little scheme. Let's do some more. So we saw numbers. So we played around with numbers, and we also looked at fixed nums and all that. Yeah. So I mentioned that these numbers are self-evaluating. So we have this idea of an expression and the value of that expression. Okay, so this is the REPL, the read eval print loop, okay, for Shea scheme. And so we have an expression, and then the expression evaluates to a value. Or the expression diverges, which means it goes in an infinite loop. Or there's an error or exception. Okay, so maybe maybe we divide by 0. Okay, get an exception undefined for 0. Okay, there's a whole lot more we could do with numbers. So there are things like, just show you one other thing. Okay, so if I divide 3 by 4, look what I get. I get 3/4, 3 over 4. All right. If I divide 3 by 4.0, I get 0.75. Okay, so scheme supports what's called rational numbers. So these are fractions where you have an integer in the numerator position and an integer in the denominator. And of course, the integer in the denominator can't be 0. We can't put a 0 here. We'll get an error, or an exception, and we can't do 0 over 0. Okay, so that's no good. But otherwise, we can put integers in the numerator and denominator, and these will be in the simplified form. So if I do 2 over 4, it'd be 1/2. Okay. So these are what are called exact numbers. So these are exact rationals. And I can convert convert from an exact to an inexact, which is the one that has the decimal point in it, by this exact arrow inexact procedure. Or if I could also do something like multiply by 1.0. Okay, so if I'm doing operations that involve inexact numbers, then basically there's a coercion that will happen. And then you can go the other way. Okay, so I can do inexact to exact. Okay. Now sometimes it, you might want to round down, so there's floor and ceiling. So maybe we want to round up. There's also round. And there's floor. I actually thought round 0.5 would go up. Oh wait, whoops. Interesting. Okay, so anything over 0.5 seems to round up, and 0.5 and below rounds down. Okay. There are other types of numbers. They're complex numbers. So, but we're not going to worry about those right now. Okay. Now, if you want to know about complex numbers, where would you turn? The Scheme Programming Language 4th Edition by Kent Divig, which is freely available online. I've given the pointer to. Or you could look at the R6RS report. Or you could look at the R7RS small report. Or you could look at R5RS report, depending on which version of Scheme you're using. Okay, so you can and should start looking these things up. Okay, so over time, I will give you less help with these things. And even now, I'm not giving you the sort of help I would if I were teaching like an intro class to people who've never programmed before. Now, maybe for whatever reason you've never programmed before, but you're still watching these videos, in which case, I appreciate your willingness to try something outside your comfort level and something that's going to be new. That's fine. There's no reason you can't learn programming from books like The Little Schemer. Or you could find a copy of, you could do things like how to design programs, right? And there are online courses for that. To learn Racket. There are resources like Learn Scheme in Fixed Num Days by Durai. There are a whole bunch of resources. Okay, you could go through SICP if you wanted to, Structure, Interpretation, Computer Programs, Scheme in the Art of Programming. There's a whole bunch of books. Simply Scheme. Lots and lots of books and resources and lots of tutorials and online things. So, no reason to be intimidated by that. Anyone can learn how to program. So anyway, we just have some numbers. So we looked at numbers last time. So now let's look at some other stuff in Scheme. So Scheme has numbers, which we've seen. We've seen a few types of numbers. Scheme also has Boolean values. Okay, so named after George Boole. Okay, so Boolean values, and in particular we have two Boolean constants. So hash f and hash t. So hash f represents false and hash t represents true. Now, it turns out that in Scheme, 5 also represents true. In fact, any value in Scheme other than hash f is considered a true value. And that includes weird values like void. Okay, so that actually constructed a value. There's a notion in Scheme of the unspecified value, sort of like the useless value you get back from certain operations that aren't supposed to return a useful value. So, void is what you do in Shea Scheme to get the unspecified value. I think that's technically how I was doing it. I'll show you something. Okay, so we're going to look at lists in a minute. I can construct a list containing this void, whatever void returns. Oh, there we go. We get this hash void thing. So we've already seen one of these hash things. And so first of all, there's hash t and hash f, right? Okay, so that's what we saw before, right? So if we look up plus, so plus is a variable bound in the initial environment to hash procedure plus. Okay, so here we have hash void, hash procedure. We also have hash f and hash t. So this is how Shea Scheme displays a procedure and this void object. Okay, but that's Shea specific. That's not a Scheme thing, as far as I know. I've certainly not an R5RS thing. I think that depends on the implementation. So there are parts of Scheme which are not specified. Certainly R5RS, that report doesn't specify a lot of things. I don't think in R6 it's specified how a procedure is displayed. You could see this is what's called an opaque object. You can't see how it adds the numbers. You can't see the actual definition of the procedure. And then this void object. All right, so this void object is something supposedly useless. So the void object is also a true value. A list containing 5, that's a true value. Okay, that list is a true value. So anything other than #f is considered a true value in Scheme. Okay, so we have numbers, we have #t and #f, those Boolean constants. And notice, just like 5 evaluates to 5, the expression #f evaluates the expression #f, or the value #f, and #t evaluates #t. So these are self-evaluating literals, the technical term. Okay, and so I've already shown you some list stuff. So there's a function called list that takes 0 or more arguments and returns a list containing those elements. Okay. There we go. Now we have a list of 4 elements containing the number 4, the Boolean literal #f, number 6, the Boolean literal #t. We could also have lists containing lists. Okay, so we have nested lists, no problem. There's also something called quote. Okay, so we can quote, let's say, cat. All right, and what we get back is what's called a symbol. Okay, this is a quoted symbol, so we get back cat. Cat is a symbol. Now we can also construct a string containing the string cat. Okay, so I use these double quotes instead of this QUOTE thing. Okay, so now I get back this string. Okay, strings and symbols are not the same in Scheme. They're different. Strings have parts. Okay, so what a string has, in this case, the string has a character C. Whoops. Okay, so in Scheme there are also characters. Okay. So the string can be thought of, the string cat can be thought of as containing 3 things: the character C, the character A, and the character T. Whereas this symbol is an atomic entity. Atomic meaning it's not made of parts. You can't tear it apart. It's just the symbol cat. And symbols in Scheme are used to represent conceptual things. Okay, so let's say if we had a chess game, okay, so the piece rook we could represent as a symbol. Now, if we were programming in C, we might have a number representing each type of piece, but in Scheme, we could have things like a symbol. Okay. It turns out that it's fast to compare symbols, whereas comparing strings is not as fast. So that's one reason to think about this, to have this. And just conceptually, this is like a type of abstraction. So we have this abstract concept, like of a cat. Okay, so maybe we have a name for a cat. Okay, so maybe we have a name, Shuggy, for a cat. Maybe we want to represent that as a string, and the concept of a cat as a quoted symbol. It's up to us. We can represent things however we want or however we find convenient. Now, we in Scheme, we tend to use symbols so often that typing these parens and QUOTE, this quote form, it's kind of annoying. So instead, we can write this shorthand. So that's quote cat evaluates to the symbol cat. Okay. In Scheme, there are also these ideas, this idea of what are called type predicates. Okay, so a type predicate is a procedure. So let's see if I just do number question mark. Okay, so we can see number question mark is a procedure in the initial environment. The hash procedure, and it's called number. And we can call that procedure by wrapping this expression in parentheses. And this procedure expects an argument, one argument. And in this case, we're giving it 5. And we can see we get back hash t, so representing a true value, saying, okay, 5 is indeed a number. And I can feed in something else. Okay, false. So quote cat evaluates to the symbol cat, and the symbol cat is not a number, so hash f. Of course, I could also write this as QOTE cat is the same thing as putting this quote mark. And the Scheme doesn't have too much syntactic sugar, shall we call it? But this is one of the examples. Is this quote mark? Okay, so there are a couple of these things. There are a couple of versions of quote, of different types of quotation, just because we use it so often. There are a few things like this in Scheme that are shorthand. In general, Scheme's quite regular. In fact, it's much more regular than most languages in terms of the syntax. There aren't many rules to keep in mind. Now, these parens tend to give people trouble if they are new to Lisps. Okay, so they want to write something like that. Notice the number of parentheses is the same. Okay, we still have 2 pairs of parens. It's just where the parens go. So here the parens go in front of the operation, okay, instead of after the name operation. So we're just putting the parens in a different place, and it turns out this will have some advantages. Now a disadvantage is, maybe we're used to writing expressions like we normally would in mathematics, like 3 plus 4. Okay, well, if we write 3 plus 4, what does it evaluate to? Well, Scheme's like, oh, okay, you're actually writing 3 expressions. Okay, so 3 evaluates to 3, plus evaluates the procedure plus, and 4 evaluates to 4. So we actually get 3 values back. Okay, this is how Shay's displaying that we get 3 different values. So instead, if we want to add 3 and 4, we have to use our prefix notation. Okay. All right. So we have these type predicates. We can also use the type predicate symbol question mark or symbol huh. Okay, is quote cat. Does that evaluate to a symbol? Yes. Now, and we'll get into this in a lot more detail. It's important to understand that this argument to symbol is an expression. Okay, so we put an expression here, and that expression is evaluated according to the rules of Scheme. Okay, and then the result of the evaluation of that expression is what symbol question mark gets and checks to see if it's a symbol or not. Okay, so we're not feeding in like a list plus 3, 4 or something to the symbol question mark procedure. Instead, plus 3, 4 is evaluating to the number 7, which is an exact integer. And then that gets, past the symbol question mark, that procedure symbol question mark. Okay, so those are the steps that happen with this procedure application. And then symbol question mark returns either hash F or hash T. Okay, so we could see that 7 is not a symbol. Of course not, right? However, it is a number. And it's an exact number. And it's an integer. Okay. We can also ask if the number's positive, and it is. Okay. So these predicates, there are lots of predicates we can use. The type predicates are things like symbol question mark or number question mark. Lets us know whether or not we have, like a type, like Boolean. Okay, well, that's not a Boolean. Hash F, is that a Boolean? Yes, it is. Okay. All right. So we have things like Booleans and symbol question mark, symbol, huh? Okay. We have these type predicates. Quite handy. There are lots of type predicates in Scheme. Okay. So we have quote. And we can quote things and quote symbols. We can also quote numbers. And notice that when we quote a number, we just get the number back. Okay. We could also write it like this. Okay. So that's what I mean when I say that 5 is self-evaluating. Okay. Sometimes it's called self-quoting. Same with the Boolean constants. Okay, so those are all self-evaluating. So self-evaluating literals. Okay, so however, if we nest the quotes, we don't get back 5. We get back quote 5. Okay, and so this quote 5, that's shorthand. That's this, that's shorthand for the output, QOTE 5. That's the same thing, right? We'll see in a minute that that's the case. So you have to be a little careful here. There's a rule. Okay, here's our rule. The rule is quote of datum. That's a singular of data. That's single data. That quote of datum evaluates to datum. Okay, so quote of 5 evaluates to 5. Quote of hash t evaluates to hash t. Quote of 5 evaluates to quote of 5. Okay, so that's our rule for quote. And so this little arrow thing, the equal greater than sign, that's my notation for evaluates tool too. Okay, we'll see that idea a lot. And then here I'm using like a little meta notation or meta META notation. So I'm just inventing some notation. It's not unusual. It's pretty standard where I'm just saying, okay, this isn't literally the symbol datum that I'm quoting. This is like a placeholder. Okay, this is like a meta variable. It's like, well, you quote anything. It could be a symbol. It could be, something else. Actually, what we're quoting here is a list, as we'll see in a minute. We quote some datum that evaluates the datum. That's our rule. Rule for quote. Okay. All right, so we saw that we could quote a datum, get get the datum. One datum we can quote is an empty pair of parens. Okay. And what does that evaluate to? An empty pair of parens. This is called the empty list. The empty list. Sometimes you might hear this called nil or null, usually nil. And in fact, in our 4RS scheme, I believe this was called nil. And in some Lisps, you would write this NIL. Okay, this is like an old Lisp idea. It's supposed to be like empty in a sense. This is like the empty list or the nil list. So you might hear people refer to this as nil, sometimes null, but usually it'd be nil. But usually, we just call it the empty list. Well, I guess we do call it null. The reason is there's a predicate. Okay. Null question mark. Yeah, so I guess we do call it null. Now that I think about it. Okay. Do we have null? Yes, we do. And remember, I can also just write this quote like this. And that quote symbol on a US keyboard is right next to the return or enter key. It's right to the left of that. Okay. Now, what about 5? Nope, 5 is not null. So null's the empty list. Okay. So we have a notion of a list. So we've seen that we can construct a list just by calling list, okay, the list procedure, and giving arguments. Okay, so here we have a list of 3 elements. So another way to construct the empty list, instead of quoting those empty parens, is to just call list with no arguments. That will give us the empty list. Sure enough. Okay. Okay, so we have the empty list, which we can get the empty list either by quoting or by calling list. Now we can construct lists that have multiple elements using this list procedure. We can construct something called a pair using cons. So cons stands for constructor. You could say that stands for list constructor, although what it actually constructs is this thing called a pair. Now, when we're constructing a list, we can use the type predicate list question mark. Oops. To see if we do indeed have a list. Yep, those are lists. Empty list is a list, okay? And there's also, not surprisingly, a predicate called pair question mark. Okay, is the empty list a pair? No, it is not. What about the result of consing 3 to 4? Yes, that is a pair. Okay, so when I cons 3 to 4, we can see that we get this interesting looking result, a pair. And so we have these parens, and we have 3, and then a dot, and then a 4. Okay, so this is called a pair or a dotted pair, cons pair. Okay. And so the truth is in in scheme, the lists, other than the empty lists, are really pairs, okay? But they're pairs of a special type. So instead of consing 3 onto 4, what if I cons 3 onto the empty list? Oh, look how it printed out. Okay, so the REPL printed out the result as the list containing 3, and I can ask list question mark list of the result. Sure enough, that's a list, even though 3.4 is not a list. Okay, so we checked. I think we checked. Let me just double check again. All right, so I think we asked if that's a list. Yeah, false. Okay, but consing 3 onto the empty list is a list. Okay, so what about whether or not consing 3 onto the empty list is a pair? It is also a pair. Okay, so what's going on? Well, what's really happening is that every time we call cons, we get back a pair, right? So that's the truth. There are two types of lists. There are the empty lists. The empty list is a list, and then there are lists that are pairs, where the second element of the pair, the cdr of the pair, if you follow that cdr, you end up encountering the empty list. Okay, so let me show you how to get the parts of a pair. For historical reasons, which I will not get into right now, read these read these papers on the history of Lisp, and you'll learn about the history of car and cdr. It's the contents of the address part of the register is what car stands for. So if we have a cons pair, so remember cons 3.4 will give us back the pair 3.4, or evaluate to the pair 3.4. So if we call car on that, we're going to get back the first part of the pair. Okay, so we'll get back the 3. If we want the second part of the pair, we use what's called cdr, CDR. That's the contents of the decrement part of the register. I think on some old IBM computer from a long time ago. So we can see that the cons 3.4 gave us a dotted pair 3.4. The car gives us the first part of the pair. The cdr gives us the rest. Now I can cons 3 onto the empty list. Now if I call car, on that pair, I still get a 3. And if I call a cdr, I get the empty list. Okay. By the way, I can also quote a pair, a dotted pair. So this 3.4, I can put a quote mark in front of it, and then we get back 3.4. Or I can use the longhand notation. Okay, that works as well. So you can quote pairs, and I can also quote the pair where we have the empty list in the cdr position, the second position. Okay, do you see how that prints out? Okay, so this prints out without a dot. Okay, so if you don't see a dot, that means it's what's called a proper list. All right, so let's try consing up some lists. That's the term schemers will use, or lispers. Let's cons up a list. So here we're going to cons up a list of link 3. The first element in the list will be 3. The second element in the list will be 4. The third element in the list will be 5. Okay. And gets printed out without any dots. Okay, this is what's called a proper list. So list question mark will return #t. So instead of building up the list with cons, I can also just quote the list. Yep, that's a list, okay? All right, so list question mark asks whether or not the object passed to list question mark is a proper list. Okay, okay, so the definition, we're ready for the definition of a proper list. A proper list is either the empty list or it is a pair. How do you construct pairs? Cons. It is a pair whose cdr is a proper list. So this is a recursive definition. Okay, so here we're constructing a pair whose cdr is a proper list because the empty list is a proper list. Or we could construct this sort of list. This is a proper list because the outer list is a proper list because it is a pair whose cdr, the second element, is a proper list. Okay? Why is this pair a proper list? This pair is a proper list because its cdr is a proper list, because the empty list is a proper list. Okay, so that's the recursive definition of proper list. If the last cdr is not a proper list, is not a proper list, like 5's not a proper list. It's not the empty list or another pair, whose cdr is a proper list. Then, first of all, list question mark will return false. And then secondly, if we evaluate the expression and see it printed out, we'll see that the result has a dot in it. Okay? Has a dot in it. So, it turns out that there sort of there aren't really lists. Okay, everything's either a pair or the empty list. What we call a list is just a special pattern of pairs and empty lists, or just the empty list by itself. So if I cons up this list, cons 3 on the cons 4 on the cons 5 on the empty list, so I get 3, 4, 5. There's no dot there. Okay. I can also I can write an expression that evaluates to list 3, 4, 5 like this. Okay, just quote it. Or I can write the quote alternatively like this. Oops, sorry. Okay. Or I can call list 3, 4, 5. Okay. Those all work. Now, another way I could write it would be like this. Sorry. I'm having a bad typing night. There we go. Like this. 3 dot pair, 4 dot pair, 5 dot, empty list. Okay, so notice how, if we go back to the cons version, both of these print out the same way. Okay. So when we see list 3, 4, 5, there really are 3 cons pairs here. It's really 3 dot cons pair, the cons pair 3 dot, cons pair 4 dot, cons pair 5 dot, empty list. It's just that it's really annoying to have to look at all these parens and dots. So the printer for the read-eval print loop will suppress the dots and the parens when you have like a proper list structure. Okay, so only put in the dots when you don't have the proper list structure. So that's why we have 3, 4, 5 as it is. Yeah, so if I put in a 6 here instead of the empty list, you'll see there's a dot there. Okay, you notice they both print out the same way. Okay. All right. So these are the dotted pairs. And the recursive or inductive definition of recursive lists. Now, there's another way to write things. So first of all, before I show you this other way of writing things, notice that if we, let's go back to the proper list stuff. Okay, that version. Okay. Yeah, let's just look at these two. Okay, so 2 ways to write the proper list, or write an expression. There are 2 expressions which both evaluate to the list 3, 4, 5, the proper list 3, 4, 5. Okay. Notice that if I look at the fully expanded dot version, there are 3 dots and there are 3 sets of parens. Okay, so those correspond to the 3 cons calls. Okay. All right, so these are equivalent. And then so for the outer cons, we have the 3. Well, that goes right there. That's the car of the outer cons. And then the thing that comes second in the cons always takes 2 arguments. That's the cdr. So the thing after the dot is the cdr. The thing before the dot is the car. Okay, so if we call car on this outer structure, if we call car on this thing, we get back 3. And if we call cdr, let's just try it. So if we call car, we get back 3. If we call a cdr, we get back the remainder of the list, of the proper list, which is the list 4 or 5. Okay, so that's the part after this dot. So this is the same as the proper list 4 or 5. And if we want to, we can then get the 4 by chaining the operator. So we took the cdr of this proper list to get the proper list 4 or 5, and then we can take the car of that list that goes 4, or we could take the cdr of the proper list to get the list 5, and then we could take the, say, cdr of that to get the empty list, or we could take the car to get the 5. Okay, so we can chain these things. Now you can see that, starting to go off the line here. So as a shorthand, scheme implementations, they define some procedures that combine cars and cooters in different ways. So if I want the car of the cooter, I can take the catter. So it's the middle names of the cars and cooters put together. So this is, the catter is the car of the cooter. So it's like I take the cooter of this list to get the proper list 4 or 5, and then I take the car of that to get back 4. Okay. And similarly, we can take the cooter, which is the cooter of the cooter, or the cadar. Now in this case, I can't do that because the car of this list is 3, and then I'm taking the cooter of that, but you can only take the cooter of a list, and you can only, or sorry, a pair. You can only take the car of a pair or the cooter of a pair, so that's not allowed. Okay, for the same reason we can't take the car of, well, in this case we're taking the cooter of 3. Yeah, it's not allowed. Okay, so we only take the car and the cooter of a pair. And we also can't take the car and the cooter of the empty list. Okay, no good. See, exception in car. Empty list is not a pair, so we can only take car and cooter of pairs. Okay. But in any case, we can see that we get this structure back, okay? So we can cons up the list, cons 3 on the cons 4 on the cons 5 to the empty list, let's say. Okay. And that's the same as doing this quote with the pairs, which is the same as doing that. Okay. We get back the proper list 3, 4, 5 in all 3 cases. Or I could write list 3, 4, 5. Okay. In all these cases, we get back a proper list 3, 4, 5. Now, let's look here at this cons version or this quoted pair version. So we're getting this structure with the quoted pair version. We're getting this structure where we have a 3 in the car of the outer pair, and then the cooter is itself a pair whose car is 4, and whose cooter is a pair whose car is 5, and whose cooter is the empty list. We can create a diagram that shows this structure. This is often called a box and pointer diagram. Okay, so I'm going to use my feeble skills to try to write this down. All right, so here we got a little example. Okay, so here's how we could write this structure with a box and pointer diagram. So we have 3 pairs. So that's what these rectangles are. So you see they're divided. So we have the car part of the rectangle and the cooter part. So the first and the rest, if you want to think of it that way. And then we've got pointers here. So the car of that first pair is pointing to the value 3. And then the cooter is pointing to another pair whose car is 4. And whose cooter points to another pair whose car is 5, and whose cooter is the empty list. So we could either point to the empty list with another pointer, often, or sometimes you see like the ground sign from electronics, or you'll see the slash, which is like, looks like a bowling score. So yeah, this is a pretty typical way of representing the structures. Now, we could have more complicated structures. Whoops. unlock that. Okay, so there's no reason. Yeah. Hold on. I'm still learning this tool. Piece of paper is better. Okay, so let me just make a copy of that. There's no reason that the car of a pair has to just be a number or something like that, right? So it could be anything. It could be a symbol, but it could also be another pair. So I could have the car of that first pair point to another pair. And maybe I have cat, dog, mouse. Oh. Stop trying to capitalize. Whew. Okay. So we could do something like that. Yeah. So let's try constructing this, structure using cons and what we know. So let's just try consing it up. All right. So cons always takes 2 arguments. And, well, we have the complicated thing here as the car, the first thing. So the first thing is whatever that is. Well, that looks kind of complicated. So let's do the rest of it. Well, the cooter is going to be a pair. So we need another cons. And the first thing, before, and then the cooter of this pair is going to be another cons pair. Another pair, so we need another cons, and the car there is a 5, and then the cooter is the empty list. So we have to quote the empty list in Scheme, okay? Otherwise we get an error. All right. So now we're back to our first cons, our car of our outer cons. Okay, so what is that? Well, that itself is just a proper list. So it's just 3 cons pairs that are we can just call cons 3 times nested. And then we have a car is going to be cat, a car is going to be dog, a car is going to be mouse, and then the empty list. So it's the same structure, actually. It's just nested. And we have the quoted symbol, cat. And we have another quoted empty list. So let me put in some new lines here. Control J. All right. So we have this cons, right? And we have the car of that cons and the cooter of that cons. So the car of that cons is when we point down here. So that points to a cons pair whose car is cat and whose cooter is a cons pair whose car is dog, and whose cooter is a cons pair whose car is mouse, and then whose cooter is the empty list. And then the cooter of the outer, or the first cons pair, is a pair, cons pair whose car is 4, and whose cooter is cons pair whose car is 5, and whose cooter is the empty list. So we actually have 2 empty lists in the structure. You can see we have these 2, slashes. Okay, so there are actually 2 empty lists here. And hit return. We see how it gets printed out. We have a list of 3 elements. Well, the first list is the list cat, dog, mouse. That's a proper list. Okay, so the outer list is a proper list, and then the car is a proper list. Okay, so remember our definition of a proper list. A proper list is either the empty list or a pair whose coulter is a proper list. So you can think about it as going backwards from, like here's the last pair in our chain, and we have the coulter is a proper list being the empty list, and then we go backwards. Okay, so this whole structure, this whole thing here is a proper list, and then the car itself, we'll look at that. That's also a proper list because we have a pair whose coulter is a pair whose coulter is a pair whose coulter is a proper list because it's the empty list there. Okay, so we end up with two proper lists, one inside the other. Okay, the dots are all suppressed, but the dots correspond really to this vertical line inside of a pair. So we have the car part and the coulter part, the car part, the coulter part, the car part, the coulter part, car part, coulter part. Okay, so the full structure actually has six dots in it. If we wanted to, quote everything, let's try it. Okay. Let's see, did I do it right? Yeah, you see it printed out the same. So the REPL printer will suppress all the dots because the car of the outermost proper list is itself a proper list, right? So we have everything's proper here. All our lists are proper lists. So all of those dots disappeared. And I said there would be 6 dots, right? 1, 2, 3, 4, 5, 6. Okay, and those, and each dot corresponds to a pair. And sure enough, there's 6 pairs. And the part in front of the dot is the car, and the part after the dot is the coulter. And so whenever the part after the dot, for example, is in parens, well, then it's a pair. And in this case, the car itself of the first pair is also a pair. So that's what, you can see that where the car of the first pair is pointing to another pair. Okay, so this is the box and pointer representation, this figure. Yeah. So we can think about it in terms of consing things up. Each cons corresponds to a dot or a box. Okay. And we can build up all sorts of structures. Now, in terms of, if we think about it in terms of StarCraft, this is sort of like a micro thing. Okay. This is like a very low level detail. And, we're dealing with dots and pointers and, these are structures in memory. Every time you do a cons, you're allocating in memory. Now these pointers, we can't do pointer arithmetic with these pointers just like we can't in Java. Okay. But these are pointers in memory. The exact representations of these things, like, whether or not there's a pointer to 4 or whether or not there's some clever, encoding in the scheme system so it doesn't actually have to have a pointer, whatever. Okay, there's some implementation details that we shouldn't have to worry about. But the point is, unless whatever the standards say, whatever the report says. Okay, so if the report leaves it unspecified, then an implementation can do optimizations or tricks. As like Kent Divig says, optimization is the art of cheating without being caught. Okay, so this is sort of an abstract notion of things, but just be aware that these cons pairs live on the heap. or live in the heap. And, so there's this relationship between these pairs, and the cons is each time you have a cons, you end up with one of these boxes, these pair boxes. And same with the dot notation, okay? So all three of these are equivalent, and you should be able to go back and forth between these, okay? So you should be able to start with this sort of diagram, the box and pointer diagram, and write the cons expression or write the quoted expression with the dots fully expanded and the empty lists where they should go, okay? Or vice versa. If you have the cons expression, you should be able to write, draw this box and pointer. Should be able to go, relate all three of them to each other. And, of course, the easy mode is I can just quote the whole thing. All right. Or I could call list. Now, if I call list, I have to make sure, to quote these symbols. Okay. I don't have to quote 4 and 5, although it doesn't hurt if I want to, because 4 and 5 are self-evaluating literals. Okay. So the easiest thing is just to use a single quote mark around the whole thing. The point is you should, be able to do all of these. You should be able to do the list version. You should be able to, figure out where, if you do the list version, where the quotes go. Okay. You should know whether or not if it matters if you do a quote for. And remember, quote for is not the same as quote for. Okay. So quote for doesn't evaluate the for, it evaluates the quote for. So we can't just add that that quote. In any case, this is something you need to get comfortable doing. Okay, so this is essential micro. This is one of the things, if you're going to use scheme productively, you need to know this and you need to be able to do it. Not just like theoretical knowledge. You should be able to do this in practice and do it in a way where you're not going to make a lot of mistakes. So it's just important that you be able to build up list structures or pair structures or whatever and read code that does this. You should be able to take cars and couters, and you should be able to, do conses, and you should be able to do quotes here. Okay. All those things are important. You should know where the dots are. You should know if you write one of these expressions down, will the REPL print out a value with dots in it? Is this a proper list or not? Okay, is it improper list? Is it a proper list? All those things you need to internalize, and you need to be able to do it accurately where you're not fumbling around. So, okay. So if you notice, I'm like pretty bad at typing on this keyboard. I'm not so great at typing to begin with, but I can tell if I'm going to make a mistake or not. I know what's going to happen, right? Like I'm not making mistakes doing this. Maybe I'm making mistakes typing because I'm bad at typing, but I'm not making mistakes because I don't understand what quote's doing or where a dot should be. Okay, that stuff I actually know. I'm just not very good at physically typing. I'll take that. So that's like kind of the macro versus the micro thing. Okay, yeah, I wish I was a little faster at typing. If I'm not making a video, I'm usually much faster. But the point is, like, I actually know what to write. I can cons up a list using cons or using a quote and dots or a quote and not dots, or I can call lists or whatever. I can cons these things up in different ways. I can write down the structure with box and pointer. I can go from the diagram to cons calls or whatever. When we're writing recursive functions, we're going to need to know that. And then there's another type of quotation called quasi-quote we'll see. So we need to know how to use quotation. We'll need to use a quasi-quote as well. We're going to be doing pattern matching over quasi-quoted expressions. If you read any papers on scheme, they're going to assume you know how to use cons. They're going to assume you know quote. They're going to assume you know what a list is, what a proper list is, what an improper list is. An improper list is just, a pair that's not proper. That's not a proper list, where you have that last cooter isn't the empty list. So another way to say it is an improper list is something that will print with a dot. Okay. So this you need to know. You need, and not like when I say you need to know, you need to be able to do it and be able to do it well, where you're not stumbling. Okay. It's up there with, you need to be able to match parentheses. You need to be able to tell if parens are missing. You need to be able to see if you need to add a pair of parens or remove parens. You need to know what has to be quoted. You need to know the empty list has to be quoted. Exception. Okay. So the empty list is invalid syntax in scheme. Well, you quote the empty list, that's fine. Okay. That's not to say that the empty list is invalid syntax in every Lisp. I'm just saying that in scheme, it's invalid syntax. Okay. So you need to quote the empty list. If you have a quoted list, well, then you don't put a quote mark inside of it, because the entire list is quoted. Okay, so you'll get back the empty parens, the empty list on its own. So this is a whirlwind tour of lists and pairs and quote and car and cooter and null question mark and what a proper list and an improper list is. Probably do a little more review and go into a little more detail. But my point is, you need to be able to do this. And so how do you learn how to do it? Well, you learn how to do it by practicing and doing exercises. This is sort of like practicing on a training map for StarCraft, or practicing against the computer. You just need to practice this some. And so when I was first learning this, I would drill myself, where I give exercises, or I would write down different structures. And we'll do some more structures like this. This one's pretty simple, actually. I would write down these sorts of structures, and then I would just kind of come up with them semi-randomly, and just write them down on a piece of paper, and then I would try to implement them using cons or using quote with the fully expanded version of the lists, with the pairs with the dots, or I would try maybe removing some dots. I would just play these different games, and I would always want to make sure that I'm predicting what I'm going to see at the REPL. Okay. And I would try to be as fast as I could be, but while maintaining, as close to 100% accuracy as possible. If you're making mistakes all the time, that doesn't help. You should be basically never making mistakes once you're into this. Okay, it should be very, very rare that you would make a mistake. And if you did see the mistake, you should immediately recognize it and know how to correct it. So you should be 98%, 99%, 99.5% accurate. After you've practiced this some. It's not okay to be 60% accurate or even 80% accurate. This is something you have to just be able to do. Okay. Very important, just because, Lisp is list processing. Okay. So here we're dealing with lists and pairs. It just comes up so often that you don't want to be fumbling with this. And I've seen this happen with someone coming to scheme from another language, and, they're trying to write a little recursive function, and they've got something wrong because they don't understand cons or quote or whatever, or they don't understand the dots and what's printed, or they don't know what a proper list is. And they spend eons, trying to write like little functions because they are little procedures because they're tripping over this stuff. And so like you have to have this part down, and so to the level where you're not thinking about it, so that when you start doing something a little bit tricky, you can think about the tricky parts and not about conses and dots and all that. In the same way for StarCraft, like you don't want to be thinking about your hotkeys or whatever, late in a game. You want that stuff to be internalized. So it's the same thing. This is kind of like our micro practice. So that's what I would do, is just like say, okay, I mean, I'll give you an example here. So let's say we want to construct a certain, nested list. So let's do quote. Okay. So this is a more complicated structure, but it's the same idea. And this is easy. This one's easy. I made it easy because it's, a proper list, and all the lists here are proper. So what do I want to do? Let's cons it up. Well, okay, so we can do this different ways. We can like one exercise is we could just, start breaking it down by like calling list. Okay, so here's an exercise we can do. Okay, there we go. And if I want to, I can add more lists. Whoops. Okay. Notice I'm having to quote these things. I have to quote symbols, and whoops, and now I get rid of that quote. All right. All right, so now I can get rid of this quote, do a list there. Okay. Let me make sure that I'm being honest here. It should look like that. Yep. Okay. Okay. Okay, so now I have replaced all the quotes on the lists, and we're, like there used to be quotes on the actual list structures, and now I'm just calling list. Okay, so that's one thing I can do. Another thing I can do is I could say, okay, well, here's a proper list. Let's replace that proper list with some conses. Okay. Yep. Notice see it still prints out the same. Okay. All right. So now I'm using Control J to put things on different lines. Okay, so here I have cons up the list. All right, so here, this list, we have a list of 2 elements, right? So we have the result of those cons, which is a proper list, and then we have the E. So let's cons up a list of length 2. So it requires this cons and another cons and an empty list. Okay, our structure looks the same. Okay, so here we have a singleton list. So that's just a cons and an empty list. Okay, so I'm just going through and I'm just replacing these structures here. So here we have a list of length 3. Okay, so we have the symbol B, and then this proper list and this proper list. Okay, so we're going to replace this with cons. I'm going to cons B onto cons. Of that proper list, what will result in a proper list, onto a cons of this expression that will result in a proper list, onto the empty list. Okay, same structure. And then I still have one list here. So let's see how many elements I have. 1, 2. Okay, so I have a list of length 2. So I could say cons onto cons. Grab that whole thing onto the empty list. Okay. Make sure I have the original structure. Okay. Looks like I got it. So I ended up replacing, the quote and all the quoted sublists with, I started doing that a little bit of time with calls to list. I got to remove some of the quotes. I had to add the quotes on the symbols. And of course, the empty list ends up having to be quoted. And then I went from list to cons, and so I was able to do that in steps. And so I was able to do it modulo my terrible typing. It's able to do it and preserve the shape. So that's an exercise you can do, right? I just made up a shape and tried manipulating. You could try doing it just with all conses. You could also try using, okay, so we could say here's the list, right? And what I want are cars and cooters to get to the C, let's say, okay? So I can say cooter of that list, okay? And so let's see here. What's the first part of that list is this inner list. So let's get the first part of the remainder. Okay. And then we need the second thing here. That's the first element. That's the car. And this is the catter. Okay. If I want to, I can use the shorthand instead of saying car of cooter of that. So the catter. Okay. And then we have a list. Well, we want the first element of that, which is the car. Okay, now we want the first element of this, which is the car. Okay, there we go. We've got C. Now I can compress some of these. So we have the car of car. That's the car. Okay, it's the same thing. Here we have a car of a cooter. So car of the cooter is the catter. Okay, still have our C. Now we could compress it even more. It turns out that the sequences of up to 4 characters are required to be in any implementation. So we should be able to CADAD. Yeah. See if this works. Yep. But I don't think we can go any further than that. I don't think Chase supports more. Let's see. I should be. Yeah. So that's as far as we can go, which is probably good anyway. It's getting a little ridiculous. All right. Now, there are other ways to try to manipulate lists and get things inside lists, and we'll do recursion and pattern matching and all that. But these are the sorts of exercises. This is the sort of thing you need to be able to do. Okay, this is like your micro training or your finger exercises for piano or whatever it is. Okay, doing your scales. That's the equivalent. Like you need to be able to cons up list structures, pair structures, proper lists, improper lists. You need to be able to predict whether or not you'll see dots in the output. You should be able to draw this sort of diagram. You should be able to go from the diagram to using cons, or you should be able to do a quoted expression that's fully expanded where you see all the dots. All those sorts of things you need to internalize. Okay, you need to know this stuff, and it doesn't take that long, but you do need to know it. Okay, so if you just like practice it a little bit, it doesn't take a huge amount of time. This is like, if you play StarCraft, let's say, you could definitely do this. Just like it'd be like practicing a build against a computer. If you play chess, or Go, or if you've learned programming, right? Like you can do it. You just have to play these games a little bit. Okay, so that's it might be a little boring. Challenge yourself, see how fast you can get. Trying these different patterns. How complicated can you get and still maintain 100% accuracy? But that's the thing. Like, you need to be accurate. It doesn't help if you're fast, if you're making mistakes. You have to not make mistakes. Okay. When we start working on recursive programs and tricky programs and all that, you cannot be having trouble with your parens, or having trouble with cons or quote or any of that stuff, or being confused because dots are appearing in the output where you didn't expect them, or because you don't know what a proper list is. Okay, you have to just know that stuff. These are fundamentals. So you have to be able to do it. And if you can't do it, and you can't do it quickly and effectively, practice and give yourself exercises. Okay, do it. Okay, I'll call this Epi 7 transcript. All right, so I'll save this session. You can see my terrible typing and everything. So you can see what I'm doing. Okay. But that's what you have to do. Now, if you're in, say, Clojure, if you're coming from Clojure doesn't use pairs, I don't think, nearly as much as Scheme does. Clojure seems to use other data structures, much more so. So I don't know. I'm kind of curious if you're coming from a Clojure background, if this is different than what you would do in Clojure. Maybe not. Maybe with Clojure, with recursion, it ends up being the same. In case, you need to be able to do it. All right, ladder practice. Practice consing up list and pair structures. Drawing box and pointer. Diagrams. Predicting whether the REPL, predicting where the REPL will print dots for improper lists. Etc. Okay. You just have to have that down. Okay. Otherwise, you're building on a foundation of sand, and whenever we get to anything tricky, you're gonna have trouble. Okay. Okay. So other ladder practice, in addition to practicing that, is to read up on lists, pairs, and proper improper lists in the Scheme Programming Language 4th edition, so TSPL 4, and read at least one scheme paper. Okay. Doesn't matter what it is. Read at least one scheme paper. It could be from Scheme Workshop. It could be from the scheme reading lists I've been showing you. It could be one of the Lambda the Ultimate papers. Anything you want. Doesn't matter. Doesn't matter where it comes from, but read at least one scheme paper. You might get stuck. That's fine. Just go as far as you can. Okay. Yeah. There you go. I think that's plenty for today, and we'll do some more with pairs and so forth, and I'll fill in some details. So I know that I'm maybe going a little fast if you've never seen any of this before, but go read up on it. Okay, there are plenty of references for intro scheme stuff. The point I'm trying to get you what I'm trying to get you able to do is things like cons up arbitrary list and pair structures in your sleep without making a mistake. Okay, that type of thing. So that's the emphasis there. It's so if you were to read, say, the little schemer, you're not going to see these dotted pairs. I don't know if you see dotted pairs anywhere in the book. Maybe they're in a frame note or something. Instead, you're going to see proper lists. But for our purposes, we're going to need to know about pairs, and also, if you're playing around with Shea Scheme, you're going to definitely see pairs. Like you will mess something up, and you'll see like a dotted pair for improper lists, or just like a pair by itself. That's not a proper list. You'd be like, what is this dot thing? Okay, what is that? Well, you need to know, and you need to be able to manipulate those. Okay. So this is important, especially when we start using quasi-quote or back quote, which is another type of quotation. And when we start doing pattern matching, all those sorts of things, you're going to have to know this inside and out. Okay. It's not that much. You can definitely do it. But it's just going to require a little bit of practice if you haven't practiced it before. And if you've seen this before and you can do it kind of, but say you couldn't do box and pointer drawings, or if you saw a box and pointer drawing, you couldn't, cons up that structure or whatever, well, practice some more and get to the point where you can just do it in your sleep. Because, we just need to do it. Need to be able to do it. It's like, knowing this is like the scheme equivalent of knowing how to make drones. You better know how to make drones, or you're gonna have a tough time on ladder. Okay, well, that's it for today, or for tonight, or for this 6:30 a.m. Have a good one. Hope to talk to you soon. Bye-bye.